Okay, we have another long answer problem here. This says two possible Lewis electron dot diagrams for fulminic acid are shown below. So we have two possibilities. Explain why the diagram on the left is the better representation for the bonding in fulminic acid. And we want to justify based on formal charges. So this is a tip-off here. There are formal charges and they are localized on particular atoms. So remember, when we want to assign formal charges to atoms in a molecule, we take a look at how many electrons they are contributing to a particular Lewis diagram and compare that to their normal valence, normal number of valence electrons. So for example, hydrogen has one valence electron, it's contributing one electron. That's neutral. Carbon has four valence electrons and it is contributing four electrons, one per bond. So that's neutral. Nitrogen has five valence electrons, but it is only contributing four electrons. 1, 2, 3, 4, one per bond. 4 is one fewer electron than its valence of 5, so nitrogen actually has a formal positive charge. Oxygen has 6 valence electrons, but here it is contributing 7, three lone pairs plus 1 in that bond. 7 is one more negatively charged particle, one additional electron, so oxygen has a formal negative charge right there. Now, let's look at this structure. Carbon is contributing 5. 1, 2, 3, 4, 5. 3 bonds and 1 lone pair. 5 is one more than its valence of 4, so that's got a formal negative charge. Nitrogen, 1, 2, 3, 4, same as before, it's got 4 bonds, so that is positive. And then oxygen has 1, 2, 3, 4, 5, 6. So that one is actually neutral this time. So in terms of, we know that resonance structures with fewer formal charges are better. They're more representative of the structure of the compound. So here we've got a plus and a minus and a plus and a minus, so we might be tempted to think, well, it's the same, right? It's the same number of charges. The thing is, the identity of the atoms that bear the charges matters. Here, the nitrogen has a plus charge in both cases, so that's no different. But we have an oxyanion versus a carbanion. We have a negative charge on oxygen versus carbon. Now, with negative charges, a more electronegative atom is better able to accommodate that negative charge. And so here, oxygen, it is better for oxygen to have a negative charge than carbon. It's very unstable for carbon to have a negative charge. So this is actually better. And so this one, yeah, because O minus more stable than C minus, more electronegative. So a more electronegative atom is better able to accommodate a formal negative charge, and that is the reason here. Now, fulminic acid can convert to isocyanic acid this way, and so it's a bit of a rearrangement here. It's a structural rearrangement. And so now, using these structures and this data here about average bond enthalpies, we want to get the delta H for this reaction. And so how are we going to get this? Now, delta H, we're using bond enthalpy data, and so this means we're doing bonds broken, the sum of the bonds broken minus the sum of the bonds formed. Those are those little sigmas, right? It's an uppercase sigma, which means add them up. So we add up all the bond enthalpies of what's been broken, and then we add up all the bond enthalpies for the bonds that are formed, and then we subtract. Then we do a subtraction, and that's how we get delta H. So what are the bonds that are broken? Okay, well, we've got an HC bond, and that is worth 413. And then we've got C triple bond N. Here's C triple bond N, and that is 891. And we've got N single bond O, 201. If we add that up, we get 1505. Now, what are the ones that are formed? We're getting an HN bond, and that is 391. We've got N double bond C, that's 615. And we've got C double bond O. 745. If we add those up, we get 1751. So that means 1505 minus 1751 equals negative 246 kilojoules per mole. So that is going to be the delta H right there. And so now this wants to know which species is present in higher concentration at equilibrium at 298 K. And we want to talk about thermodynamic favorability and the equilibrium constant. So delta H, this is oh, sorry, we skipped one. A student claims that delta S for the reaction is close to 0, so change in entropy. And we want to explain why this is accurate. And so when we're talking about entropy, we're talking about dispersal of matter and energy. And so there are two ways that entropy can increase. Either there can be a decomposition reaction or some way that a greater number of moles of product are produced. So we have X moles of reactant, and then the number of moles of product is a greater number. So that would be a dispersal of matter. We can also have a phase change from going from solid to liquid or liquid to gas or solid to gas. Those are all entropically favorable, and those would be also a positive delta S. And then negative would just be the reverse. But here, neither of those things are happening. It's just a structural rearrangement, right? So it's not even that this is breaking apart or anything like that, or molecules are coming together. It's just these four atoms, and then they just rearrange the way that they're bound. And then we're also not changing phases. So same atoms, no phase change. Right? So with entropy, we're thinking about numbers of molecules, and we're thinking about phase as well. And so neither of those change. So from there, that's important because we're trying to talk about the thermodynamic favorability and the equilibrium constant. And so what we're saying is if delta S is approximately 0, then delta G is approximately delta H, right? Because delta G equals delta H minus T delta S. So if delta Z is about 0, then this term pretty much goes away. And so delta G is roughly delta H, and here's delta H right here, right? We just got it, negative 246. And so that's negative. This is the forward reaction is exothermic and favorable and spontaneous, right? Delta G is negative, right? So negative delta H means it's exothermic. Negative delta G means it's spontaneous. So if one direction is spontaneous, then the opposite direction is probably not very spontaneous. And so what this means is that this side is favored, right? Let me put that a different color. This side is favored, and therefore will be at a higher concentration. Now, the other way to justify it mathematically is to say that delta G equals negative RT ln K. And so in order for delta G to be negative, the way that logs work, we're going to need a positive K, we need a K that is greater than 1, right? Only if the K value is greater than 1 will this produce a negative delta G, and what that means is that products are favored, right? And so if products are favored, the product will be at a higher concentration at equilibrium. So that's a little bit of thermodynamics tucked in there. Now let's look at just a little more stuff. We've got the ammonium salt of isocyanic acid, and that's the product of the decomposition of urea, represented here. A student studying the decomposition reaction runs this at 90 Celsius, and then we've got concentration of urea as a function of time. So starting out with this initial concentration, and then that is depleted over time. Time is in hours, 10, 20, 30 hours. So the student proposes that the rate law is rate equals K times urea concentration. Now, how does the data support this? So the way we want to look at this, they make this nice and neat for us to get half-lives, to get the half-life. So what we're going to notice here is we start at point 1, and then when do we elapse one half-life? That's going to be after 10 hours, right? So T 1/2 is 10 hours, because after 10 hours we've got half, and then after another 10 hours we have half again. After another 10 hours we have half again. And we know that if the half-life is constant, then it is first order. That's something we know about a first order reaction, is that it will have a constant half-life. And so that makes sense, because this rate law is outlining a first order relationship, right? Because we have urea concentration and it is not raised to an exponent here. And that makes sense, by the way, because this is a decomposition reaction. So only the concentration of the reactant, of the lone reactant, should be a factor. So now we can very quickly also determine the rate constant, because the rate constant is going to be equal to 0.693 over the half-life. So let's put 10 hours, and we'll put a little dot here to signify that's 2 sig figs, because we're going to get 0.069 inverse hours. 0.069 per hour. That would be the half-life there. So this is an easy number to remember, 0.693. So K equals this over half-life. That will be a useful equation. Then finally, the student learns that the decomposition reaction was run in a solution with a pH of 13. Briefly describe an experiment, including the initial conditions that you would change and the data that you would gather to determine whether the rate of the reaction depends on the concentration of hydroxide. So this is actually extremely straightforward, right? They're telling you it's being run at a pH of 13. How would you figure out if this changes by changing, or depending on the concentration of OH? Well, let's just change the hydroxide ion concentration, or which means change the pH, right? If we do that, we'll get the answer, right? How do we figure out whether the rate of the reaction depends on the concentration of hydroxide? Change the concentration of hydroxide, right? That couldn't be more straightforward. Make sure to leave other variables constant, like temperature. We don't want to change the temperature. That would make it impossible to compare our data to the original data set. But change the pH, try it at 12, then try it at 11, try it at 10. Those are different hydroxide ion concentrations, and we'll see if the rate changes. So that was a good one. We went over a bunch of different stuff here, and that was a good long answer problem.